Now we just looked at solving a system of equations by graphing. So if I have two equations, I can graph them, and remember, if I want to find the solution to the system, the solution is the point that the two equations have in common. However, if I'm looking at a graph, it might not always be obvious where two lines cross, especially if they're not crossing at integer values. So then we kind of need another way to solve systems. So today we're going to look at two additional ways to solve systems. And one of those ways is, you may have guessed it, yes, he's waiting to substitute into the game. So substitution is another way to solve a system of two equations. So here's a system. If I want to solve a system by substitution, really there's a couple steps we need to go through. The first step is that you want to solve for one of the variables. So if I'm looking at this system and I want to solve for either x or y, I'd maybe be drawn to the second equation, and that should be fairly easy to solve for y there. All I would need to do is subtract 1. So this second equation I'm just going to rewrite as y equals 3x minus 1. So there's my second equation just rewritten, y is solved for. And that's really the first step. Now, I'm going to take that 3x minus 1, and that's equivalent to y. So if 3x minus 1 equals y, anytime I see y, I can go ahead and substitute 3x minus 1 in for y. Or really, this is almost like copying and pasting. I'm cutting out that y and I'm replacing it with something that it's equivalent to. Then the second step is I'd actually need to go through and rewrite that equation. So my first equation would now read, I have 2x plus 3 times y. Well, what is y equivalent to? Y is equivalent to 3x minus 1. So there's my substitution. And then all of this equals 19. So I've just rewritten that first equation with 3x minus 1 substituted in for y. Here, now this equation is in one variable. So I can go through and solve 2x plus 9x minus 3 equals 19. Combine your like terms. Add 3. And x comes out to be 2. Now the last thing is, once I know x is 2, I just need to go back to one of my original equations and substitute in 2 for x. So I can really pick any one of these three equations, the first one, the second one, the third one, substitute in this 2. I'm going to maybe pick the second one. Just in case if I rewrote the third one wrong, I'm going to stick with my original. So let's now plug in 2 for x. So y plus 1 now equals 3 times 2. And y should come out to be 5. So my solution should be, if x is 2 and y is 5, that's the point that makes both equations true. Now I just substituted into this second equation, right, to find y. So I'm actually going to go back to the first to check my answer. So here's a great check. If you look at that first equation, 2x plus 3y equals 19, if I substitute in 2 for x and that 5 for y, does 2 times 2 plus 3 times 5 equal 19? Yes, it does. This is a true equation. So that point, if I plug it back in, it should make both the first and the second equation true. I can check here, plug in 5 for y, 2 for x. Does 5 plus 1 equals 3 times 2? Yep. That point makes both equations true. That's the solution to the system. So let's just look at a general recap here. And no, there is no substitution for butter in my heart. So substitution, step 1, solve for one variable, substitute it into the other, solve the new equation, and then once you have found that variable, substitute it into one of the other original equations to find the second variable. So now let's look at something like this. Maybe pause the video and write this example down. And once you have this written down, let's all kind of follow this together. There's a couple different places I could start. I could probably solve for m pretty easily. But let's look at the second equation. Let's just say I start here and I decide to solve for m. So what I do to the left, I do to the right. I'll divide by 2. So if I divide everything by 2, make sure you're dividing that term with the n and the 16. Both of those need to be divided by 2. So if I divide everything by 2, I should have 5n minus 8. So this is the second equation right here. I've just rewritten it. So now my new system, I guess I can rewrite it if you want. So first equation I haven't done anything with. Second equation I just divided everything by 2. Okay, so here's my equation. Now if I'm going through and substituting, m is by itself, so I'm going to take all of this and replace it anywhere I see an m, which is right here. I'm going to replace it with what it's equivalent to. So here comes the substitution. I now have, we'll go up here, 5n minus, so what is m equal to? M is equal to all of this stuff, 5n minus 8. So I'm subtracting that whole thing, and then that should equal 8. Now, caution, please make a note of this. I see this mistake all the time. I'm subtracting all of this, so I would actually have to distribute that negative. So this is like 5n minus 5n minus negative 8. If I'm subtracting a negative 8, that'd actually be like adding 8. So make sure this is like a negative 1 here that you'd be distributing into the parentheses. And all of that should equal 8. So if I go through and solve, let's see, 5n minus 5n, those will just cancel. And I'd be left with 8 equals 8. Okay, well, what does this mean? My variable's actually gone. The n has disappeared, and I have 8 equals 8. Does 8 equal 8? Yes, it does. And actually, anything I plug in for n here, those values would cancel out, and I'd still have a true equation. So this means this is a case where there's actually an infinite number of solutions. Does this mean anything for m, anything for n is a solution? No. Think back to when we graphed lines. It was if I had two equations that were actually the same line, any point on the line was a solution. So if I look back at these two equations right here, these are actually the same equation. They're just rewritten. If I took this and let's see, if I subtracted m and added 8, though they're actually the same equation. So if I say there's an infinite number of solutions, it's really any value that makes this equation, these equations true are solutions. If I have m and n, if I wrote it as a coordinate, I just write it in alphabetical order, so m first, then n. So let's just see, I mean, if I plug in 7 for m, right here I'd have 7 equals 5n minus 8. If I go through and solve this, it looks like n would be 3. This would be one possible solution. So any point, any coordinate that makes the equations true, that would be a solution. And in this case, there's an infinite number of solutions. Really, any coordinate that makes the equation true would solve the system. Or excuse me, any coordinate that makes the equation true would solve the system. So now on to our third method of solving systems. Survivor, is this show still on TV? I think maybe. Do they still do the elimination round? So third method is elimination. The goal of elimination is to eliminate a variable. So if I was given a system like this, this might not be the nicest to graph. This might not be the nicest to do substitution on, because if I'm looking at these equations, if I try to get x or y by itself in any of these equations, I might be dealing with lots of fractions, and it just might not be very slick. So elimination is going to be an option. If I'm solving a system by elimination, the goal is to get opposite coefficients on one of the variables. So let's just say I wanted to eliminate the x term. Well, I'd look on the coefficients on the x, and I'd want to know what's the smallest number that both 4 and 5 divide into? And that would be 20. So 4 times what is 20? Well, that would be 5. 5 times what is 20? That would be 4. If I go through and I multiply these equations by 5 and 4, then I should have close to opposite coefficients, but not quite. 5 times 4 is 20. I want this to look like negative 20. So I would have to make one of these negative. I'm going to make the second number negative. And then follow me here. This is what elimination looks like. So I'm going to multiply the first equation by 5. And I need to multiply the left and the right side by 5. So I would have 20x plus 15y equals negative 5. And then in the second equation, I'm going to multiply the left and right by negative 4. If I multiply the left, I have to multiply the right. And let's see, negative 4 times 10 would be negative 40, and negative 4 times a quarter is negative 1. So we'd have negative 41. And here's really the goal. So the whole reason that I multiplied these equations by 5 and negative 4 were so I could get an opposite number in front of the x term. At this point, now that I have opposite coefficients, I can just go ahead and add. If I add down, the left side cancels, or excuse me, the x's cancel. And on the y's, I'd have 23y. So if I add the left side of the equation, I'm just left with 23y. If I add the right side of the equations, I would have negative 46. And then if you divide each side by 23, y would be negative 2. Now what happens once I've solved for one of the variables? Well, just like we did with substitution, now I'm going to go here. If y equals negative 2, pick either of the equations. I'll just pick the first one and substitute in negative 2 for y. So now the first equation would look like 4 times x plus 3 times y is actually negative 2 now, equals negative 1. And if we go through and solve, x comes out to be 5/4. So as a coordinate, if x is 5/4 and y is negative 2, if I plug that point into both equations, the equations should be true. Therefore, that's the solution to the system. Now, just as a quick check, I've gone back to the second equation. I've plugged in 5/4 for x, negative 2 for y, and I get to this point right here. 25 plus 16 would be what? 41/4? And 41/4 is the same as 10 1/4 or 10.25. So, yep, this equation is correct. I can be pretty confident in my answer. Now, I want to point out just another scenario that could arise when solving a system by elimination or substitution. So why don't you pause the video at this time and think of what you could multiply these equations by to get opposite coefficients on the x or the y. If you eliminated the x, let's see, 6 and 9 both go into 18. So if I want to make this coefficient 18, I can multiply by 3. And I can multiply the second equation maybe by 2. And maybe you decided to eliminate y. You may have actually chosen the same numbers if you were trying to eliminate y. So let's just go through with this. So distribute the 3, multiply everything in that first equation by 3. Everything in that second equation by 2. And then if we add down, you'll see, okay, well, wait a minute, the 18s cancel and the 6s cancel. So I'm left with something like 0 equals 65. Is that true? No way, this is never true. So this is a case where 0 never equals 65. This is actually a no solution. or the null set. There is no point that would be on both of these lines. If you went through and graphed these lines, you should find that the lines are actually parallel. They're never going to intersect. They have no points in common. So if these come out to be the same number, infinite number of solutions, if I get something like this, 0 equals 65, that's never true. This would be a no solution case. Last example, a group of 40 children attend the Red Hawks game on a field trip. Each child received either a hot dog or a bag of popcorn. Hot dogs were $2, popcorn's $1.50. If the total bill was $71.50, how many hot dogs and bags of popcorn were purchased? Here I am down at the field at the Red Hawks game, riding a tricycle. I think I won that competition. Probably got some free Wild Wings or something from the Red Hawks game. So the first thing I might do if I'm attacking this equation is what is this word problem asking? So if I'm attacking the problem, I'd be looking kind of at this last question right here. I want to know how many hot dogs and bags of popcorn were purchased. So I'm just going to write this out. Let H equal the number of hot dogs and let P equal the number of bags of popcorn. And I'm wondering if you could write a system of equations that would relate all of this information. So pause the video and see if you can give that a shot. So if each child either receives a hot dog or a bag of popcorn and there's 40 children, then together the number of hot dogs plus the number of bags of popcorn should equal the total number of kids. Then I've also got a bunch of prices up here. I have $2, $71.50, and $1.50. $2 per hot dog. So the total cost of the hot dogs would be $2 times the number of hot dogs. $1.50 times the number of bags of popcorn, and altogether I have, the bill was $71.50, and this is your system. Now you could go through and solve this by substitution or elimination. Just a word, if I were solving this by elimination, you really only have to multiply one of the equations. So if this is 2 and I want this coefficient to be -2, if you were choosing elimination, you just have to multiply the top equation. This would be pretty easy to solve by substitution also. You could solve this for H or P very quickly. So choose whatever method you want. If you go through and solve, you should get the same answer. I'm just going to go ahead and use elimination. So I'm going to multiply that top equation by -2. Then I'd be at this point. The h's would cancel if I add. -2 plus 1.5 would be -1/2. So -1/2. And -80 plus 71.50 would be -8.5. And oops, -1/2 p, excuse me. So to get p by itself, divide by -1/2. Dividing by -1/2 would be the same as multiplying by -2. So the number of bags of popcorn should be 17. And the number of the number of hot dogs would be 23. And those two should add to 40.